All right. So we've been talking about three different pathways by which ATP is made. We talked about the production of ATP from creatine phosphate. We talked about anaerobic glycolysis, and we talked about aerobic respiration. We're going to talk about the latter two of those in this series or in this part of this lecture. And regardless of which one that we're talking about, anaerobic glycolysis or aerobic respiration, we have to begin with glycolysis. Right? So that's where we're going to start. And remember that that word glycolysis literally means the splitting of sugar. Glyco means sugar, gluco, glycogen, so on and so forth. And lysis means to break apart. So in this step, in this first part of this, we're going to be breaking apart sugar. Okay, a couple of things to remember about this. The first is that we do not need mitochondria and we do not need oxygen. So mitose and oxygen are not required. And this process takes place in the cytoplasm of the cell. Okay, so we're looking here at the cellular cytoplasm, and we're looking at enzymes that are suspended in that cytoplasm that are going to cause this process to kind of continue on. Okay. Now, we're going to follow a molecule of glucose through this pathway. And glucose, as you know, has a 6-carbon sugar, right? C6H12O6. What we're primarily interested in here are the carbons. So we're going to go ahead and make glucose here. We're going to make 1, 3, 4, 5, and 6 carbons, right? So here is glucose, our 6-carbon sugar. And very generally speaking, what's going to happen during this process is we are going to split glucose into 2 3-carbon molecules. These 3-carbon molecules are called pyruvate or pyruvic acid. Okay, and this is very generally speaking what happens during glycolysis. You can see that the process lives up to its name. Right? Now, this arrow that I've drawn right here, okay, this arrow that I've done to sort of draw this process, this is actually, I'm condensing 10 different biochemical steps. Right? So there are 10 steps here. We're going to talk about one of them specifically in a little while, but I don't really want you to memorize all 10 steps. When you take biochemistry or you take another physiology class a little bit later on, you're probably going to be asked to memorize those 10 steps. But I'm more interested in the big picture that we have here. So for now, know that there are 10 steps there, but ultimately glucose is converted to 2 pyruvic acids or pyruvate. Okay. The chemical formula for glycolysis is a little bit more detailed than what I've drawn here. I do want to take a look at it just really quickly. So we have glucose. We have 2 molecules called NAD+. This is nicotinamide adenine dinucleotide. We have 2 ADP. We have 2 inorganic phosphate, and that yields for us those 2 pyruvate. We have the 2 ATP, and then we have 2 NADH plus, I'm going to run out of room, 2H plus 2 water. Okay, so this is what our equation for glycolysis looks like. Just a reminder, you'll notice that there is no oxygen in this equation because this process does not require oxygen. All right. The net yield from this process, again, to remind you from the last lecture that I had posted on YouTube, the net yield here is 2 ATP, all right? It turns out that the gross yield is actually 4 ATP, but 2 are used in the process, so the net is going to be 2, all right? However, the reason that I'm focusing on the equation is not to focus on the lack of oxygen, it's not to focus on the ATP. What I really want you to pay attention to here is I want you to pay attention to this nucleotide here, nicotinamide adenine dinucleotide, NAD+, all right? And I also want you to focus on this guy right here. These are the things that I want you to focus on. Because what we're doing in this process is we are splitting glucose into 2 pyruvate acids, and we are producing a couple of ATP in the process, right? But what we're also doing is we're starting to take electrons off of glucose, and we're starting to transfer them to these nucleotides that are high energy electron carriers, right? So what we see happening during this process is we see a transfer of electrons, all right? What I'm doing is I'm taking electrons off of glucose and I'm transferring them to these molecules right here, okay? You'll notice that NAD has a positive charge here, meaning that it has an extra proton, all right? When I add an electron to a proton, I get a hydrogen, okay? So what I'm doing is I'm taking an electron off of glucose, adding it to NAD+, and that gives me NADH, all right? And my yield here is 2 NADH. These are what we call high energy electron carriers, and they're going to become really important. They're going to become an important part of the story as we start to discuss the latter parts of this process. But for right now, I want you to pay attention to the fact that we are creating NADH. We're creating these high energy electron carriers in this process, right? And we're doing this via a really common thing that we see in chemistry as well as in biology. We're doing it through what we call reduction oxidation reactions. When I take an electron off of something, in this instance I'm taking an electron off of glucose, I say that that thing has been oxidized. Oxidation. I just start that over. Oxidation, right? I say that that thing has been oxidized. So in this instance, what we're doing is we are oxidizing glucose, and we're transferring that electron or adding that electron to NAD+. When something in chemistry gains an electron, we say that it's been reduced, or that's a reduction. Okay, so we have these two processes going on here. Okay, glucose is being oxidized and NAD+ is being reduced. Glucose is being oxidized, NAD+ is being reduced. I'm saying that multiple times because it's really important that you're clear on what's being oxidized and what's being reduced, because we're going to be going through this process and multiple examples of this process for the next couple of lectures. All right? As a result of the fact that we're always taking an electron off of something and adding it to something else, we always have these reactions coupled with one another. So we have reduction, oxidation, reactions, oxidation. Why am I having a hard time with that word today? Reduction, oxidation reactions. When we mash up those terms, we call them redox, right? Those are redox reactions, and they're always going to be coupled with each other. What we're doing here is we're taking the beginning of the term reduction, the beginning of the term oxidation, and we're adding them together to make redox. And that's what we have happening here. So while we are producing a couple of ATP from glycolysis, the important thing to remember here is that we're also storing some of that energy that we found in that glucose molecule in these high energy electron carriers, these NADH molecules. All right? Okay, so with that in mind, let's go ahead and start a little bit of bookkeeping. All right, what I want to do is I want to keep track of what we're making through this entire process so that we can kind of come back to it as we need to, and we have a place to sort of write all of this down. So what I'm going to do here is I'm going to divide this sheet of paper here in half, and I'm going to start a summary. And what I want to do in this summary is I want to write down the process, right? I'm going to write down what I've used, what I've made, and then the net yield. So the first thing that I want to summarize here is I want to summarize this process of glycolysis. Okay, and whoops, let me go ahead and head my columns here. So I'm going to go ahead and say what's been used, what's been made, and what's the net. Right? So I'm going to go ahead and take a look at that here. So in glycolysis, we are using 2 ATP. I told you that even though that equation I showed you was the net equation, there are 2 ATP used during glycolysis, and we make 4. Then we also make 2 NADH. Okay? So our net here is 4 minus 2. Our net is 2 ATP and 2 NADH. Right? So we've begun the process of glucose breakdown, right? We've split that glucose into 2 pyruvate molecules. We've made a couple of ATP directly from that glucose. We call that substrate level phosphorylation because we're directly making ATP from the fuel molecule itself. All right, so we have 2 substrate level ATP that are made, but we're also starting to store some of the energy that was found in that glucose molecule in these high energy electron carriers, and those are going to become important later. So we're left now with 2 pyruvate molecules. Oops. What happens to that pyruvate next? This process is called Pyruvate Fate. I'm going to go ahead and put this summary sheet aside. We're going to come back to that. And the next thing that we want to look at here is Pyruvate Fate. So, in other words, what happens to pyruvate next? Okay? And the answer to that question depends on whether or not oxygen is present or oxygen is absent, right? So if oxygen is absent, we follow one pathway. And if oxygen is present, we follow another pathway. All right? So this is kind of like the choose your own adventure books that we had when we were kids. Maybe you didn't read those, but I checked, I think, just about every single one that I had out from the library. All right? So if oxygen is absent, what is going to happen? Well, if oxygen is absent, we're going to enter what we call anaerobic metabolism. Okay. This is what happens when we're in trauma, when we're in heavy exercise or something like that. Right? When you are exercising very, very, very heavily, you very likely are entering anaerobic metabolism. And if that happens, if oxygen is absent, the pyruvate is going to get converted to lactic acid. So I'm going to get converted to lactic acid, or lactate. And that's what we have happening here. Okay? There's an enzyme responsible for this conversion. That enzyme is called Lactate Dehydrogenase, or LDH. We talked a little bit about that when we talked about isoforms and isozymes in the last section in class. All right? So what's happening during this process? All right? The biggest thing that's happening during this process is that we see another redox reaction occurring. We see NADH. And these are those NADHs that we made when we made the pyruvate getting converted back into NAD+. Okay? NADH is getting converted back into NAD+. And this is critically important here. All right? This is critically important because if oxygen is absent and we're metabolizing glucose into pyruvate, what we're doing is we're using up all of the NAD+ that we find in the cell, and we're converting it to NADH. Right? So if nothing were to happen and we just used up all of that NAD+, eventually the process of glycolysis would be forced to stop because there would be none of these left in the cytoplasm. However, by converting pyruvate back into lactate, what happens is that we recycle that NAD+, right? Here what we're doing is we are removing an electron from NADH, so we're oxidizing NADH, and we are reducing pyruvate to lactic acid, all right? And that's really, really important. So this process is going to recycle NAD+ back into cytoplasm. Okay, recycles NAD+ back into the cytoplasm. Now, of course, the problem with this is that we're also building up lactic acid or lactate in our muscles and in our other tissue. That drop in pH causes all sorts of problems that we'll sort of discuss later, so this is not sustainable. Because of the reduced pH that we have from lactate. So it's an effort to sustain this process by recycling NAD+, but unfortunately that buildup of lactate becomes somewhat problematic and we eventually have to halt the process. All right? So in this next lecture, what we're going to do is we're going to take a look at what happens if oxygen is present in the cell.